Today I am going to discuss about phase controlled converter. Last class I have discussed about single phase half controlled rectifier with inductive load. There we have seen that because of the inductor voltage, some extra conduction of thyristors. Now today we will discuss about full wave rectifier. Here the output voltage is twice that of the half wave rectifier. At the same time, as the load is inductive, the frequency of the ripple current is twice. So this single phase full wave converter or control converter are generally preferred over single phase half control converter. Some more interesting features of this single phase full control converter, let's see. Before starting single phase full wave controlled converter, let's see a little bit about single phase half wave uncontrolled rectifier. Here in the circuit you can see sinusoidal AC voltage is connected across 4 diodes. Now this AC input is working as a bridge in between the two legs. Leg 1 diode 1 and 4, leg 2 diode 3 and 2. So the AC input is working as a bridge. That's why the name is full bridge rectifier. And as diode we are connecting, so it is also known as single phase full bridge uncontrolled rectifier. In positive half cycle of the input voltage, diode 1 and 2 will conduct, and in negative half cycle 3 and 4 will conduct. So both positive and negative half cycles are rectified to produce DC output voltage. So AC input we are getting rectified DC output voltage. Let's see the waveform. Here the top waveform is of AC input voltage. You can see between 0 to pi the voltage is positive and pi to 2 pi it is negative. So between 0 to pi there is favorable condition to conduct for diode number 1 and 2, and from pi to 2 pi diode 3 and 4 will conduct. So in both half cycle positive output voltage we will get. So 0 to pi 1 and 2, pi to 2 pi 3 and 4, then again 1 and 2, 2 4 3 4. So likewise it will continue, and rectified output voltage we will get. Here you can see the frequency of the output voltage is twice that of the input voltage. Likewise we can say the frequency of the output current is twice that of the input voltage, and it is twice that of half wave rectifier. So this advantage can be used in case of inductive load. Generally, to reduce the ripple current, if the frequency of the current is more, then filtering requirement will reduce. So this will be one of the advantage in case of single phase full wave rectifier to reduce the ripple of the output voltage. So we will see in case of inductive load. Let's proceed from. It is single phase full wave controlled rectifier. Only difference is that diodes are now replaced by thyristors. Now in case of thyristor we know that we have flexibility to select the triggering angle. In the positive half cycle, thyristor number 1 and 2 is triggered at pi by 6. Then as the load is resistive, so it will continue till pi. So from pi by 6 to pi, thyristor number 1 and 2 will conduct. Then the 5 pulses are given to thyristor number 3 and 4 at 7 pi by 6. So in the negative half cycle, thyristor number 3 and 4 will conduct to give the output voltage, and 3 and 4 will conduct from 7 pi by 6 to 2 pi. Then again at 13 pi by 6, or you can say it is equivalent to pi by 6, or new AC cycle starts from here. So likewise it will continue and output voltage you will get. Here the output voltage frequency is twice that of the input voltage. Output current frequency is twice that of the input voltage. Now single phase full wave control rectifier is connected across RLE load. Here this RLE load can be assumed as a motor load. R is the resistance of the winding, L inductance of the winding, and E back EMF developed by the DC motor. In earlier classes we have seen that whenever inductance is there in the load, then some extra conduction period we will get across the thyristor. Here also same thing we will observe. Let's trigger the SCR 1 and 2 at pi by 6. Then the SCR will continue to conduct till favorable condition is there. Now you will see that in negative half cycle at 7 pi by 6 firing pulses are given to 4 and 3. Then if there is stored energy across the inductor and the inductor voltage minus source voltage is still positive, then the net voltage between inductor and AC input will not allow thyristor to off. In the negative half cycle, thyristor number 3 and 4 are triggered. Now, when the AC input voltage is reversed from pi to 2 pi and at 7 pi by 6, thyristor number 3 and 4 is triggered. Then you can see from pi to 7 pi by 6, though the thyristor number 1 and 2 is under reverse bias condition, but because of the net voltage between inductor and input voltage, thyristor number 1 and 2 continue to conduct from pi to 7 pi by 6. As soon as this thyristor number 3 and 4 are fired, now current is getting less impedance path through thyristor number 3 and 4. So the current will shift from thyristor number 1 and 2 to 3 and 4, and you will get the output voltage from 7 pi by 6 to 13 pi by 6, and that 13 pi by 6 is equivalent to your starting point of the AC input voltage, that is pi by 6. So you can see here that across the output voltage two similar pulses we are getting during a complete time period 360 degree. That's why this kind of converter are also known as single phase two pulse converter. At the same time, the frequency of the output voltage and the output current is twice that of the input voltage. Let's see this waveform along with output current. Here you can see that at pi by 6 output current starts, and we know that in case of inductive load the load current lacks the supply voltage. You will see that the peak of the load current or the output current is achieved at later time than the input voltage. So the output current is lagging the supply voltage by certain rate. Now observe the duration between pi to 7 pi by 6. Between pi to 7 pi by 6 output voltage is negative but output current is positive. So the multiplication of this voltage and current, we can say the power is negative. As the power is negative, we can say the power is supplied from load to source, and from pi by 6 to pi voltage and current both are positive, so power is multiplication of voltage and current is positive. So one of the interesting feature of this inductive load is that some of the power is transferred from load to source. So from pi by 6 to pi, power is transferred from source to load, and from pi to 7 pi by 6, power is transferred from load to source. Now let's find the important parameters: average output voltage, RMS output voltage of this single phase fully controlled rectifier. So average output voltage we can write as V0 is equal to 1 into 2 divided by 2 pi. 2 pi is the complete time period. As we are getting two similar pulses in 360 degree, So it is to be multiplied by 2. So we will find average output voltage of one pulse and multiplied it by 2. So the range of this output voltage following the input voltage is pi by 6 to 7 pi by 6. So the expression we can write 2 by 2 pi by 6 to 7 pi by 6 Vm sin theta d theta. Now let's generalize this one. If the SCRs are triggered at alpha, then average output voltage is 1 into 2 by 2 pi alpha to pi plus alpha Vm sin theta d theta, and you will get 2 Vm by pi cos alpha. Likewise, we can find RMS output voltage, that is equal to V0 R 1 into 2 by 2 pi range alpha to pi plus alpha Vm square sin square theta d theta, and you will get RMS output voltage equal to Vm by root 2. So today I have discussed about single phase fully wave rectifier, then single phase fully controlled rectifier, then single phase fully controlled rectifier with RLE load. And we have seen that in case of inductor, some of the power is transferred from load to source. Then we have found out average output voltage and RMS output voltage. In coming classes, you will see some more features of this controlled rectifier. Thank you.